Good morning, everyone. Today, Andrew and I will be presenting our thesis titled Simulating an Inland Waterway, a Predictive Traffic Model of the Upper Mississippi River. We would first like to acknowledge and thank our principal advisor, Professor Golden. No, it's good. Our reader, Professor McMahon, and our editor, Professor Lutz. We'd also like to thank Coach Harris for his help over the last 4 years and helping prepare us for this presentation. And last but not least, William Webb for the opportunity. Today, I will start off with a discussion of the background of our thesis. Then, I will state our objectives and move into theory, method, and procedure before handing the presentation to Andrew, where he will discuss the case study, conclusions drawn from it, and recommendations for future work. We will take questions after Everett and Aiden's presentations. The Upper Mississippi River is a critical corridor for inland freight in the United States. It runs roughly 660 miles from St. Louis, shown here, where the river splits off to the Missouri River, up to Minneapolis, Minnesota, shown here. The lower Mississippi River contains no locks, so the focus of our thesis was solely on the UMR. The system that is used today was largely built in the 1930s under the Rivers and Harbors Act. This established a requirement for a channel 9 feet deep throughout the whole river. To aid in this transit, 29 locks and dams were constructed to traverse the approximately 1,200 feet of elevation change throughout the river. While standard tows in the 1930s would max out at 500 feet in length, today commercial tows often exceed 1,000 feet, while the chambers were built to be 600 feet in length. This means that operators have to decouple their tow, pass it through in sections, and reassemble on the other side. This process, also known as a double lockage, increases wait times and creates a cascading delay effect across the entire system. Locks 20 through 25, which still operate at their original 600-foot chambers, have been identified by the United States Army Corps of Engineers as a highest concentration on the river and a bottleneck. The federal response to this problem is the Navigation and Ecosystem Sustainability Program, NESP. It was authorized by Congress in 2007 and calls for the construction of new 1,200-foot lock chambers at locks 20 through 25. Locks 26 and 27 already operate with 1,200-foot chambers. Lock 27 was built that way in 1953, and Lock 26 was replaced in 1994. Despite being authorized in 2007, the NESP received little dedicated funding for over a decade. The Infrastructure Investments and Jobs Act in 2022 changed that, as it moved several projects into active construction. The most significant milestone is Lock 25, where foundation work and early concrete placements are underway. Jacob Dilliston previously built the foundation for us with his 2023 thesis titled Simulating Inland Waterways, a microscopic model of inland waterway traffic flow. It was comprised of a discrete element framework in Excel and VBA, which gave him some issues. His study focused on the Ohio River, and with that, he identified 4 major improvements to be made. His first recommendation was to improve the simulation of locks. Secondly, he recommended improving the prediction and movement of tows. Third, relating to the second, he thought applying weather delays would help increase accuracy. And finally, he recommended switching over to a multi-threaded programming language. We will tackle his final recommendation first. While Dilliston simulated using Microsoft VBA, we used Python instead for several reasons. VBA is a single-threaded program. A multi-threaded program, such as Python, allows it to run multiple tasks at one time. Additionally, VBA was built specifically for Microsoft applications, whereas Python is a general-purpose programming language. Finally, Python has a giant ecosystem of libraries, meaning we have many tools to choose from. With background solidified, we can introduce our objectives. Our objectives with this thesis are to accurately predict delays on inland waterways because of locks, weather, traffic, and maintenance. We also want to determine the effect of investing in upgraded infrastructure, specifically larger locks with auxiliaries. Before continuing, I would like to outline more specifically what I will discuss further. I will introduce how our data is collected and processed. Then, I will move into the simulation, its environment, and the system behavior as a whole. I will conclude with showcasing the user interface. Data collection was a critical first step in building an accurate and reliable model. Most of the raw data comes from the U.S. Army Corps of Engineers. Navigational charts were used to define the physical geometry of the river system. This includes the channel layout, distances, and radii of the river. A navigational chart can be seen on the right. This specific chart is a 10-mile segment of the UMR around Lock 11. Bridge locations were also gathered, which act as a small constraint along the river. River conditions. Lockage records provide detailed information on vessel movements through the locks. They provide timing, queuing behavior, and throughput. River conditions are also gathered, and this gives information on the condition of the river, such as water levels and flow rates. All of this data is organized in Excel and shipped as an Excel file to the Python simulation. Once the data is combined and imported, there's still a lot of preparation before running the simulation. The files are combined and cleaned. This means removing information and filtering out unrealistic values in the data. They are then organized into groups based on how the vessels behave. The upstream and downstream traffic is split. Those two groups are then split based on the vessel size and location along the river. This is important as a large tow moving upstream behaves much differently than a small tow moving downstream. The river conditions are used to create a velocity factor that correlates with the observed tow speed to quantify how weather conditions shift vessel performance. Inland waterway traffic differs from highway or rail systems as the movement is constrained by fixed bottlenecks, the locks and dams. Instead of modeling aggregate flow, this simulation uses an agent-based approach, where each tow is treated as an independent object with its own state. All tow characteristics, such as direction, barge count or size, position, and velocity, are sampled from Empirical Lock Performance Monitoring System data, LPMS. This ensures that the simulated traffic reflects real operational patterns as opposed to theoretical assumptions. To show you what I mean about agentic simulation, here's a figure showing the life of tow 573-22879 from our simulation. This tow starts its life here at mile marker 263, a randomly sampled starting position. Its mission is to travel upriver, which it immediately begins doing. Once it reaches a lock, represented by these horizontal dashed lines, it is halted until it finishes waiting in queue for any other tows and completing a lockage. It spent 4 time steps at this lock, lock 24, which is equivalent to 1 hour. This process is repeated with each subsequent lock until it reaches the end of the modeled river section here, mile marker 379. During the simulation, a number of tows are simulated until you get something that looks like this. Here it can be seen that multiple tows are heading different directions and locking at different time steps. Another way of observing tow behavior is looking at the velocity of tows over time. Let's take a look again at our favorite simulated tow. Tow number, everyone with me, 573-22879. Thank you. You can see that at the start, the velocity is 0. The tow quickly accelerates to its top speed of 7.7 miles per hour, shown here. This is defined by the LPMS data for its number of barges, direction, position, and weather effects. The velocity drops steeply when it reaches its first lock here and remains at 0 until it is finished locking. So what's going on here at time step 31? Why does the speed decrease, then return a time step later? This occurs when the vessel is in traffic. At time step 31, the tow passes its friend, tow 44262-727, and both tows are slowed to the first quartile speed from their respective LPMS data. Vessels slow down when they're within half a mile of each other, according to the Cole regs for inland river navigation. The simulation is organized into 3 layers. The user interface allows parameter change without modifying the code itself. The model contains static system definitions. These include river geometry, lock dimensions, and bridge locations. The simulation engine drives the computation and advances each tow at 15-minute intervals, called time steps. At each time step, it updates positions, evaluates lock and bridge interactions, processes queuing behavior, and records the state of the system. This separation improves flexibility and allows different infrastructure scenarios to be tested with the same framework. The behavior of the system is driven by 3 key mechanisms. First, vessel speed varies with local river geometry, specifically the channel width and bend radius, as well as river speed. We adjust for this using regression relationships from the observed data. 2, lock operations are modeled using LPMS timestamps, which capture both queuing delays and lockage durations. And 3, 600-foot locks introduce a major constraint with the decoupling of tows. This increases service time, the backing up of tows, and the effects compound, so delays at one lock propagate downstream. Shown now is the user interface. This, along with the user guide in the thesis document, allows the user to update the program to run how they choose. On the left are all the different tabs that can be interacted with. It is split into 2 categories, data inputs and simulation. We will first focus on data inputs. These allow the user to update both information about the tow, weather conditions, as well as physical geometry of the river. Currently, lockage data is selected. Lockage and river data are edited by either loading a CSV file or clearing the data. They have the option to add data all at once or one lock at a time. Here, the lock and dam data tab can be seen. The bridge and map data tabs are similar and allow the users to add, edit, delete, or clear the current geometry. Scrolling to simulation, we can see the chief drivers for what can be changed given a certain river geometry and data files. Here, the number of runs and number of 15-minute time steps are manipulated. Below that is the start and stop mile marker along the river. Next, the density, meaning traffic, and weather z-score can be updated. Finally, the downed and upgraded lock boxes are shown here. They house a drop box, allowing the selection of any locks in the simulation. These will update if any locks are created or deleted in the previous tabs to allow those new locks to be put down or upgraded. The second tab in the simulation category is the Report Output tab. This allows the user to select what they would like to see in the report that is generated by the simulation. I would now like to hand the presentation over to Andrew to discuss case study, results and conclusions, and recommendations for future work.
Thank you, Caleb. The case study for this thesis was run on the Upper Mississippi River over a 220-mile section. A month of data from late 2025 was used along a stretch of the river from mile marker 159, shown here, to mile marker 379, shown there. This stretch contains locks 20 through 27 for a total of 7 locks. Locks 26 and 27 have been upgraded to have 1,200-foot lock chambers, while the other 5 have 600-foot lock chambers. This provides a natural comparison between older and smaller locks and newer upgraded infrastructure. Traffic was almost split evenly by direction in this sample, with 51% of tows traveling upriver and 49% traveling downriver. The most common tow configurations were 0, 6, and 15 barges, and, as expected, the downstream river traffic traveled faster. To validate the system, we ask, does the simulation do what it was designed to do? We do this by comparing simulation data to the LPMS data with 2 tests. First, the Kolmogorov-Smirnov, or KS test, and second, the Mann-Whitney U-test, or MW test, also known as the Wilcoxon rank sum test. The KS test measures the largest distance between 2 cumulative distribution functions, also known as CDFs. 2 example CDFs are shown on the right. The red CDF is the original CDF, and the blue CDF is the simulation CDF. The KS statistic is the largest difference between these 2 CDFs shown here. The MW test ranks each value in 2 distributions and sums them, then compares the difference between them to a critical value. To validate our tool, 4 key metrics were tested: queue time, transportation efficiency, tow speed, and lockage time. 3 simulation cases were run against the historical LPMS data: a 1-day 96 time step simulation, a 1-week 672 time step simulation, and a 1-month 2,880 time step simulation. The 1-day simulation most closely resembled the LPMS data and even passed the MW test for tow speed. No other variables passed these tests. This means that the simulation models tow speed and efficiency well in the short term, but that errors compound, leading to worse results for longer duration simulations. These test results indicate that the behaviors predicted by this tool are statistically different than the historical data. and we cannot say that the predicted results resemble real-life behavior. Our validation reveals we were not able to create a numerically accurate simulation. However, we have still accomplished our goal of improving the accuracy from previous work. The previous work measured the MW test results for each lock in his 4-lock simulation, which we can compare to the MW test results for all 7 locks in our thesis. As you can see, although we are still 7 orders of magnitude from realization, we have increased accuracy by at least 6 orders of magnitude. We can see part of the reason why these tests failed here, with a graph of the number of active toes over time for the LPMS data. Notice how much variation there is. There can be as few as 3 active toes, or as many as 30 active toes at any given time. Now, let's look at the graphs produced by the simulations. You can see that as more time steps are simulated, an equilibrium number of 26 active toes is reached in the system. This equilibrium is reached after 400 time steps, or 4 simulated days. It is clear that there is much less variation in the number of active toes over time in the simulation data. The lack of variation is caused by using a uniformly random spawn rate. This is important because variation in toe count causes backups in the simulation, which increases the time that toes spend waiting in queue. We can see this effect in the time breakdown of these data sets. The time spent moving is in Webb Institute blue, the time spent queuing is in red, and the time spent locking is in yellow. Although the portion of time spent locking by the real-life LPMS data is very similar to the simulation data, the time spent in queue and time spent moving are drastically different. To achieve accuracy in future iterations, the simulated time in queue should be increased. Now, let's compare the CDFs visually, starting with queue time. This is where the largest error was found among the 4 metrics. The bluish line is the simulation CDF, and the red dashed line is the LPMS dataset. The time spent queuing by the simulations is far shorter than the LPMS dataset, although this increases with more time steps, since there is more time for the toes to reach the locks. Next, let's compare toe speed. The simulation CDF is once again blue, and the LPMS CDF is red. The CDF for toe speed remains relatively consistent throughout the simulations and is less normally distributed than the LPMS dataset. Transportation efficiency is a measure of barge miles per minute, or the velocity of cargo. The transport efficiency CDFs are closely tied to the LPMS data, but don't match the shape of the distribution. The efficiency metric is the most important metric, since that is how we determine the impact of changing different factors. An ideal river system moves barges at the highest overall average velocity. The most interesting validation metric is lockage time. While at low time steps, the simulated CDF for lockage time does not follow the LPMS CDF behavior. The simulation behavior is very promising at greater durations, mirroring the LPMS dataset well. Although our simulation did not produce realistic results, we can still use it to predict the impact of different scenarios. The next step in our thesis was to use our tool to forecast how changing different factors would affect our results. We created 4 different specialty cases, one for upgrading lock 25, one for closing lock 21, one for increasing traffic density by 25%, and one for a 95th percentile storm current. Lock 25 is currently being upgraded and is expected to finish being upgraded in 7 years. From our analysis of LPMS data, the upgraded locks seem to be about 50% more efficient per barge. The figure on this slide shows the mean decrease in lockage minutes from a 600-foot lock chamber to a 1,200-foot lock chamber for each tow size. You can see that for tows with 0 or 1 barge, the 600-foot lock actually takes less time to perform a lockage, since 600-foot chambers fill and drain more quickly. Once a tow has 2 barges, however, the average tow locks 7 minutes faster on a 1,200-foot lock. This trend continues for tows with more barges. The graph only goes up to 9 barges, since beyond 9 barges, a tow must decouple first to pass a 600-foot lock. Up to 15 barges can pass through a 1,200-foot lock at one time, which was simulated in this case. The next case was the Lock 21 closure case. Lock 21 breaks down around once a month for a mean duration of 13.5 hours, or 54 time steps. We simulated this closure to begin about halfway through the simulation, shown by this bump in the figure. Our model predicted that although the lock is only closed for 13.5 hours, the effects of the closure remain in the system for another 61 hours. This decreased efficiency and increased overall time spent queuing. For our increased traffic case, we increased the traffic density by 25% to test how this would affect the simulation. We can see that the tool functioned properly by looking at the figure, which shows 25% more active tows over time than the base case. From this simulation case, we saw a 54% increase in queuing time and a decrease in overall efficiency of 5%. Lastly, we tested a 95th percentile weather case, where flooding widens the river and increases the river current. This case was created by looking at the relationship between volumetric river flow, river depth, and average tow speed. The relationship we measured in the original data told us that when the river current increases, tows traveling downriver are about twice as affected as tows traveling upriver. We think that this is because tows traveling upriver tend to increase their fuel usage to maintain schedule, while tows traveling downriver tend not to decrease their fuel usage as much, accepting it as a bonus. The figure on the right shows the velocity of tows upriver in blue and downriver in red. Now, watch as the original data is overlaid onto the figure. You can see that the simulation functioned as intended, decreasing upriver tow speed and increasing downriver tow speed. The case study results for efficiency are shown here. Upgrading Lock 25 led to a 0.21% overall increase in efficiency, and closing Lock 21 for 54 time steps led to a 0.15% overall decrease in efficiency. This seems insignificant, but is actually a large volume of cargo. Since more time is spent in queue in real life, the effects of upgrading Lock 25 and closing Lock 21 are likely even more significant. A 25% increase in traffic density decreased transportation efficiency by 5%. The increased river speed increased transportation efficiency by 4.5%. These results are interesting since weather has a much larger impact than expected. Although the severe river current case shows a more efficient river system, this does not mean that the tows themselves are more efficient, since tows traveling upriver must burn more fuel to maintain their speed. Shown here is a breakdown of how time was spent by tows in the different cases. The time spent moving is in blue, queuing is red, and locking is yellow. Upgrading Lock 25 decreased queuing time by 6% relative to the base case. Closing Lock 21 for 54 time steps increased queuing time by 1% compared to the base case. Increasing traffic density by 25% increased time spent queuing by 54%, which decreased time spent moving by 4.4% relative to the base case, which explains the 5% decrease in efficiency. The heavy weather case decreased time spent moving by 1.7% since tows moved faster overall, which increased efficiency. In conclusion, we've continued Jacob Dillson's work to predict delays on inland waterways. We used Python for this and performed a case study of the upper Mississippi River, which we validated. We used our tool to predict the impact of different delays and forecast the impact of upgrading Lock 25. Our recommendations for future work include increasing the accuracy of our simulation, reworking the weather delay system to analyze each section of river independently, changing how tugs are spawned and despawned to better account for variation, and testing multiple bodies of water against longer duration data sets. It would also be interesting to test a case with increased traffic density and upgraded infrastructure to see how much more traffic can be supported by the upgraded locks. Thank you for attending this presentation. Please hold all questions until the other presentations are complete.